Hi, Chem Kids. So now that we've spent some time learning about different states of matter and solids, liquids, and gases, and what those different states of matter look like on a molecular level, we're going to start thinking about what happens as we change between those states of matter. And for today's discussion, we're going to think about water, which we often think of in a liquid form. But we're going to think about what's happening as we heat up those molecules and they change to a gaseous form, what we think of as steam, or as we cool down those molecules, slow them down, and it turns into a solid like ice or ice cubes. Although we're going to be thinking in terms of water, these heating curves can be drawn for any substance as we heat it up and cool it down, but we're just going to use water as our example for today. So before I show you what a heating curve actually looks like, I want us to spend a little time predicting or brainstorming what a heating curve may look like before you see one that's already completed. So a couple important things to know before we begin is what the axes on the heating curve look like. It's basically a graph, and so there's a y-axis and an x-axis, and this is already drawn on your paper for you. And this x-axis down here, this is telling us basically what's happening as heat is added. So we're adding heat as we go across the x-axis. Some people think of this almost like time. So basically as we heat it up or more time takes place, we're going this way on the graph. At the same time, things are also happening on the y-axis. And the y-axis is telling us what the temperature of the substance is. So we're thinking about water. It's like if you had a thermometer in the middle of that cup of water or that beaker of water, it's telling us the temperature of the substance. So this axis is the heat added, and this axis is the temperature of the stuff we're studying. So before we start, I want you to make a prediction. So this is going to be your prediction graph. This is at the top of your note sheet, and I want you to actually draw one on before we start. This is an important thing so you can think through what you think is going to happen. And for what we're going to be studying, we're going to be thinking about water, and we're going to start down here. So everyone's graph is going to start down here, and you're going to think about having a cup of ice cubes with a thermometer right in the middle of all those ice cubes, and you're going to start here. And what I want you to do is draw some graph on this empty space of what's going to happen to the temperature of those ice cubes as you add heat. So take a few seconds and draw a graph somewhere on here. What's happening to the temperature as you add heat or as time goes by. So press pause until you've finished drawing your heating curve, and then you can continue with the video. So I hope by now everyone has a prediction drawn on their graph. Some of you might have something that looks a little bit like this. As you increase the temperature and heat it up, going this way, the temperature of the substance should go up. So some of you probably have a graph that looks something like this. Some of you might have also drawn a curve. So maybe it got steeper or maybe it got flatter, but you have some sort of curve going up and to the right. And others might have had something that's less of a straight line or a curve, and maybe there were some sections to it like this. Maybe you had some flat sections called plateaus. So maybe you were in one of these categories, or maybe you have something totally different, and that's cool too. But this is giving you an idea of, in all of these example predictions, the temperature of the substance is definitely going up as you heat it up. And we should all know that from middle school science. As we heat something up, the temperature, as measured by a thermometer, should be increasing. So as time goes up, the temperature is going up. So in this slide, we're going to go through all the different parts of an actual heating curve, and again, we're going to think about water. So even though our general idea is that the temperature has to go up, it's actually a little bit more elaborate than you may have originally thought. So we're going to break it down step by step, and you can take notes at the bottom of your sheet, and you definitely want to fill in an example of a heating curve somewhere on your note sheet, and I think there's a space for you to do that. So just as a quick reminder from the notes you've already taken, we just want to review what's happening at the molecular level, because you want to keep that in mind throughout our study of heating curves. So we have solid ice cubes. Again, this isn't the best picture of the water ones, because as you know from looking at the simulation, water actually is a little bit more spread out when it's frozen because of those hydrogen bonds. But for our sake, we can think about solid substances being packed together, slow-moving particles. When we have a liquid, they're a little bit more fast-moving, they're spread out, they can flow by each other, so this is a liquid. And then when we have a gas, like something like steam, the particles are moving very quickly and they're very spread out, and they're making lots of collisions with each other and the sides of the container. Throughout our discussion of heating curves, you want to keep in mind these molecular view or particle view images. So as we discussed, we're going to start down here and we're going to think about having a beaker full of ice cubes. And so those ice cubes are at a very low temperature. They're very cold, and we have our beaker of ice cubes with a thermometer in them. And so we stick that beaker right on a hot plate, and what immediately starts happening as we add heat through the hot plate or the Bunsen burner? You're correct. The temperature is going to start going up. And so we see this positive slope, this increase in temperature because we're adding heat, so the temperature is going up. And this should be exactly probably what you predicted to happen in some form with something like this, that the temperature is going up. And some of you might have thought that it would just continue to go up and you'd have this straight line. But actually something really interesting happens after a certain amount of time. Because all of a sudden the temperature can no longer go up for those ice cubes, and instead you're going to see a plateau. And the temperature is actually going to stay the same. And you're not going to see a change in temperature for a little while because all of this heat that you're adding is going into a phase change. And so this plateau, this is really important, this plateau is a phase change. And at this moment, what's happening is the energy that was going into heating up the particles is now being used or focused on overcoming the bonds that are keeping those particles close together. So we remember that the solid particles are really packed close together, but our liquid particles are more spread out. So this phase change is getting us from this molecular view to this molecular particle view. So the phase change is the flat part because the energy isn't being used to raise the temperature, it's being used to overcome the bonds holding those particles together. And what's this phase change called? Well, we're going from a solid to a liquid, so this is going to be melting. So at this point in the phase diagram, we've now melted our substance. So what happens next? After that phase change is complete, you have liquid water. So we have a bunch of liquid water in our beaker, and so what's going to happen as we continue to add heat? Exactly. The temperature of that liquid water is going to go up and up and up. So we have another increase in our temperature. But eventually, no matter how long you heat up that beaker of water, and maybe some of you have done this in a middle school science class, but you're heating up the water, you're adding more and more heat, that hot plate's really working, and you're going to get to a temperature, and then you're no longer going to see an increase in temperature. It's going to stop. It's going to, exactly, once again, plateau. And you're not going to see any change of temperature in your beaker of liquid water, because when you get to this point, all of the energy that you're adding, all of the heat that you're adding is going into overcoming those bonds holding together the liquid particles. So we have our liquid particle view right here, and here's our gas particle view. So obviously something needs to happen, or energy needs to be added in order to get from this particle view to this particle view. And that's what's happening in this plateau, or that phase change. So this is once again our phase change area, and what do we call it when a liquid goes to a gas? We call it vaporization or evaporation. So this is our liquid to gas section. So now you have steam. By the end of this plateau, you're completely converted, or the beaker is completely converted from liquid water to all now steam or water vapor. And then we're going to continue to add heat and heat that up, and the temperature of the steam is actually going to rise, and it's going to get hotter and hotter. So this is the overall view of any heating curve. We're talking about water, but this would be true for any substance. So we're going to just go through it one more time very quickly. You start down here because you have a solid that the particles are close together, they're moving very slowly. You start to add heat, and so the temperature is going to go up and up and up until you hit a plateau. Once you hit the plateau, all of that energy is being used to overcome the bonds holding the particles together, and you have melting in your beaker of no matter what substance you're talking about. So you're going from a solid particle view to your liquid particle view, and that's what's taking place on that plateau. You continue to add heat, and your liquid's going to increase in temperature, so your liquid substance is going to heat up until you hit another plateau. During this plateau, all of your liquid is changing into a vapor. That's what's taking place on this flat section. It could be a short flat section or a long flat section, depending on how much energy is needed to convert from liquid to a gas. So by the end, we have this gaseous particle view. Now, another way you could think of it is instead of adding heat, you could actually take away heat, and we could think about it going this direction. So instead of increasing the temperature, we could decrease the temperature. So let's talk through that. Well, you start with a gas, and you start removing heat, and it's cooling down. And you cool down until all of that energy being removed is turning it from a gas particles, so really spread out and moving quickly, to liquid particles, more condensed together and moving a little bit more slowly. Then you continue to cool down and your liquid substance is going to cool down until you get to freezing. So as you go the other direction, your phase changes are the opposite. So this would be condensation if you're going in a cooling direction, and this would be freezing or solidification if you're going in the cooling direction. So you want to ask yourself, which way are you going? Are you heating things up, and so you'd be moving in this direction, you're adding heat? Or are you cooling it down? Are you removing heat, and then you'd be going in this direction? So depending on which direction you're going, your phase changes are going to be either melting and evaporation, or condensation and freezing. Now, for most substances, we actually know, by knowing something about their properties, exactly what temperature these plateau areas will occur at. So if we're thinking about H2O, or water, we know that H2O freezes and melts at exactly 0 degrees Celsius. So that plateau is going to occur exactly at 0 degrees. And we know that it will boil or evaporate at 100 degrees Celsius. So no matter what science class you're in or what you're doing, if you have pure water, and we're saying pure H2O, and you put it in a beaker and you heat it up, so you're in this phase right here, you're heating up a liquid. The hottest temperature your beaker of water will ever reach is exactly 100 degrees Celsius. And then it will start to turn into a vapor and boil, and then it will turn into steam. So you're never going to have a beaker of pure water that's 101 degrees or 102 degrees. So no matter how long you sit there with your hot plate, you're going to increase the temperature to 100, and then all that energy is going to go into a phase change until you're looking at an empty beaker because all of the water has evaporated and turned into steam and water vapor. So depending on what's in your beaker, if you have salt or other substances added to your water, you might be able to get over 100 degrees, but pure H2O will always have this plateau happen at 100 degrees. Now, other substances obviously melt and boil and freeze at different temperatures than 0 and 100 degrees. So this is only an example of H2O's heating curve. Other substances might have a much steeper initial area, or they might be much flatter. Their plateau could happen at 50 or 150 or 3 degrees. So it really depends on what the substance is, but all of the substances will have this general format of an area of increase, a plateau, an area of increase, and a plateau, and another area of increase. So this is the last slide in our presentation, and hopefully by now you're like, oh, thank goodness, yours was so sloppy, you're terrible at writing on an iPad. I agree, I'm trying to get better. But this highlights a lot of the most important information packed into a heating curve. We've seen what it looks like just bare bones, but this has all sorts of great visuals and information packed into it. So a few things I want to draw your attention to. One is it shows us the particle view. When it's a solid, it's really the particles are packed together and they're moving very slowly. A liquid, they're spread out and moving more quickly. And then a gas or vapor, they're much more spread out and they're moving very quickly. I also like this diagram because it points out the phase changes. So it's really important to remember that if you see a plateau, that means a phase change is happening. And you need to know which phase change is happening depending on if you're heating up or cooling down, or if you're between this area of increase in this, or this one and this one. So you want to know your phase changes. You want to remember what they're called. You learned about that earlier in this lesson. And you also want to know when they occur on a heating curve. And the last thing I like about this is it shows that you can read a heating curve in two different ways. You can read it going this way, and so you're adding heat or energy, and it's increasing the temperature of the substance, and you're going from a solid to a liquid to a gas. You can also think of it, though, as a heating curve that's showing what happens when it gets cooled down. So this is you're starting in a gas, and you're cooling down to a liquid and then a solid. So there's two ways to read a heating curve, and both of them have similar information, but you want to remember which direction you're looking in when you're considering what's happening in a lab, or if you're reading a heating curve on a quiz or a test. So I'm going to leave this up to end the presentation in the nice clean format, so hopefully you can jot down some notes if you need to finish your notes. There's also some readings on the module if you feel like you still need some explanation for heating curves. Thanks for sticking with this. I appreciate your patience as I figure out this tool, and I will see you guys next time in class. Have a good afternoon. Bye.